My name is Brendan Allen, and I'm presenting the paper titled Robust Cadence Tracking for Switched FES-Cycling with an Unknown Time-Varying Input Delay using a Time-Varying Estimate. My co-authors are Kimberly Stubbs and Dr. Warren Dixon. To motivate this paper, we need to first understand neuromuscular disorders. Neuromuscular disorders impair the voluntary function and control of muscles. They arise due to problems with the brain, nerves, or muscles, and they can be caused by either genetics, disease, or injury, and these disorders affect people of all ages. A consequence of these neuromuscular disorders are that people experience movement disorders. In extreme cases, they may result in partial or total paralysis. As a consequence, there are negative secondary health effects, for example, in sedentary lifestyle. There may be social repercussions, and some even require constant assistance or oversight. Overall, there's a degradation in the quality of life. In the United States alone, there is estimated direct and indirect costs that exceed $161 billion a year. Neuromuscular disorders have numerous causes. For example, there's stroke, traumatic brain injury, and spinal cord injury. In addition, there are numerous neurological diseases such as spina bifida and multiple sclerosis. Overall, neuromuscular disorders have left millions of people disabled throughout the world. To combat the severity of disability, various rehabilitation methods have been examined. One promising method is functional electrical stimulation, or FES. FES applies an electric field across a muscle to elicit an artificial involuntary muscle contraction. There are numerous health benefits of FES, for example, improved motor or muscle control, and increased muscle strength and range of motion. In addition, FES has been shown to increase neuroplasticity. Importantly, neuroplasticity is the mechanism through which the body is able to relearn. However, there are numerous challenges. For example, there are uncertain and nonlinear dynamics and time-varying behavior as a result of fatigue. There also is an input delay. This input delay can potentially destabilize the control system and must be considered. The input delay causes further complications for a switch system that switches between motor and FES control. For example, the delay must be considered to properly schedule when to apply the stimulation so that muscle contractions do not occur in antagonistic muscles. In this paper, a cadence tracking controller that is robust to an unknown time-varying input delay is developed, and delay-dependent trigger conditions are developed to schedule the activation and deactivation of the FES and the motor. The contribution of this paper is that a time-varying estimate of the delay is included, and trigger conditions were improved to reduce residual forces in antagonistic muscles. The combined cycle rider dynamics are shown. They include human input torque that results from the FES-induced muscle contractions. And notice the delay dependence. There's also a motor input, there's inertial effects, centripetal Coriolis effects, gravity effects, viscoelastic tissue effects, which result from having a human in the loop, and they are both force length dependent and force velocity dependent. There's cycle damping and disturbances, which may result from muscle spasms or spasticity or any human adjustments. The same combined cycle rider dynamics as before are shown. Now we will expand the control torques. First, we have the human input torque that is comprised of stimulation of various muscle groups. In this paper, we stimulated the quadriceps, the hamstrings, and the gluteal muscle groups. The human input torque is comprised of individual muscle control effectiveness multiplied by a delayed FES input. And the motor torque is comprised of the motor control effectiveness multiplied by the current input. The control torques can be further expanded. For example, the delayed FES input is comprised of a selectable constant multiplied by a switching signal multiplied by the control input. And the current input is comprised of a selectable constant multiplied by a switching signal multiplied by a control input. The switching signals are shown, where Q denotes the angle of the crank. The set QM represents the set of crank angles where it is effective to stimulate a given muscle. Recall that the set M represents the quadriceps, hamstrings, and gluteal muscle groups. KDZ stands for kinematic dead zones, and the set Q KDZ represents the set of crank angles where it is kinematically inefficient to stimulate any of the muscle groups. Q alpha is a trigger condition that adjusts the activation and deactivation of the FES input by using the delay upper bound. Q alpha effectively projects Q forward such that if stimulation is applied at angle Q, then the associated muscle torque will occur before the angle Q alpha. To better understand the switching conditions, a few examples will be demonstrated, but first let's understand the image that is shown. Notice that the crank is being separated into various regions, the FES regions and the kinematic dead zone regions. If the FES-induced delay was assumed to be negligible or non-existent, then the stimulation of a given muscle group would occur whenever the crank is in that muscle's FES region. Likewise, the motor would be applied whenever in a kinematic dead zone, and no FES would be applied. However, since the delay is not negligible, the above switching conditions were designed to adjust the activation and deactivation of the motor and FES to compensate for the delay. Now let's look at a few examples. First, let's assume that Q is at 180 degrees as shown, and that Q alpha happens to be in the shown location. Notice that Q alpha is in the hamstring FES region. Therefore, the hamstrings would be stimulated, and the other FES muscle groups would not be stimulated. Likewise, we can see that Q is in a kinematic dead zone, and so the motor would still be turned on. This is because although the hamstrings are being stimulated, there is no guarantee that the muscle contraction forces are occurring yet, and so the motor is on in order to maintain control authority. Now we will look at another case. Let's assume that Q has moved forward and it is now in the hamstring FES region. Likewise, let's assume Q alpha has moved forward, but that it is still in the hamstring FES region. Therefore, since Q alpha is still in the hamstring FES region, FES should still be applied to the hamstring muscle group. By looking at the motor switching signal, we can see that Q is in a FES region and stimulation is actively being applied, and therefore the motor can be turned off. Notice that by design of sigma m, whenever Q initially enters a muscle's FES region, that muscle is guaranteed to be producing a muscle force, and since stimulation is maintained until Q alpha leaves the FES region, the muscle force is still present when Q alpha leaves that FES region. This allows control authority to be maintained when the motor is turned off. Now the last case will be considered. Let's assume that Q has moved forward, but that it is still in the hamstring FES region. Likewise, let's assume Q alpha has moved forward and is now in a kinematic dead zone region. Therefore, FES is not applied to any muscle group, and the motor is turned on. Notice that FES inputs will cease the instant Q alpha first enters a kinematic dead zone, and due to the delay, muscle forces would still be present. However, since the FES is no longer providing an active control input, the motor is activated. The error system will now be considered. First, we define the position error, E, which is the desired position minus the measured position. Then we define an auxiliary error term called R, which is comprised of a cadence error term, a position gain term, and a delay compensation term. The delay compensation term EU is defined as an integral of previous FES inputs, which integrates from t to t minus tau hat, where tau hat is the delay estimate, and a composite error vector z is defined as shown. The open loop error system is shown. Notice that the last term is a result of using a time-varying delay estimate, where tau hat dot is chosen by the control designer. The term chi is shown, and chi can be upper bounded as shown. The FES and motor controllers are defined as shown. A common Lyapunov function candidate is defined as V sub L. Recall that the control objective is to achieve cadence tracking, or to minimize E dot. Therefore, E, R, and EU are included in the Lyapunov function candidate to be able to show that E dot is bounded. VL can be bounded by the following bounds. Additionally, the terms Q1 and Q2 are LK functionals and are used to facilitate the subsequent stability analysis. The main result of the paper is summarized in Theorem 1, which states, the closed-loop error system is semi-globally uniformly ultimately bounded in the sense that is shown, provided that certain gain conditions are satisfied. Notice that Y includes E, R, and EU, which are required to show that E dot is bounded. A quick sketch of the proof will now be provided. Since the motor controller is discontinuous, a generalized solution to the time derivative of the Lyapunov function candidate exists almost everywhere. The set value derivative is shown. The input delay is represented by the term r sub tau, as is highlighted. EU dot is now represented by the highlighted terms. Recall that EU was designed to compensate for the delay. Notice that from EU dot we get a minus r squared term. However, it comes at the cost of a positive r squared term. Additionally, we can see a tau hat dot term that will need to be dealt with. Q1 dot is now shown by the highlighted terms. Notice that Q1 dot has positive r squared terms, but also negative r tau hat squared terms. Q1 dot is used to cancel out all of the positive r tau hat squared terms. However, again, this comes at the cost of creating positive r squared terms. Q2 dot is now shown by the highlighted terms. Even though it is difficult to see in this form, Q2 dot is used to upper bound the derivative of the Lyapunov function by minus EU squared, minus Q1, and minus Q2 terms, which is critical to the result of the paper. Again, this comes at the cost of positive r squared terms. A major challenge for input delayed systems is that the poison is in the medicine. That is to say, the input is how we achieve our desired results, but the input is delayed, which causes complications. Recall that from EU dot we had the term ilm alpha 2 ksr tau hat minus ilm alpha 2 ksr. To achieve a bounded result, the negative term has to dominate this positive term. To help combat this complication, the highlighted term is added and subtracted. Now the highlighted term allows for alpha 2 to be designed to minimize this r tau hat term, which allows for the negative r squared term to dominate the positive r squared terms, which otherwise would be impossible. An added benefit of adding and subtracting the aforementioned term is that the highlighted term can now be minimized by implementing a better estimate of the delay. This is a primary motivator for implementing a time-varying estimate of the delay, because the delay is known to be time-varying. To validate the aforementioned control design and stability analysis, a preliminary experiment was performed on a single participant using the FES cycle that is shown. For the preliminary experiment, FES inputs were provided by placing electrodes only over the quadriceps muscle group and connecting them to the stimulator shown. For crank position and velocity feedback, an encoder was implemented at the crank. In the preliminary experiment, the delay was estimated by first using a constant estimate of the delay and measuring the delay before and after 2 minutes of cycling. The rate of change of the delay was then calculated. Then this rate of change was used to implement a time-varying estimate of the delay. Before the experiment, the participant was seated in the FES cycle and the electrodes were connected. The participant was then asked to be passive and to provide no volitional effort. A controller was then used to ramp the cycle up to 50 RPM, at which time the designed control system was implemented for 2 minutes. Note that the participant in this video has spina bifida and needs a wheelchair to get around, and he is providing no volitional effort. The shown figure and the subsequent figures are from the experiment when the time-varying estimate of the delay was utilized. Recall that the designed control system was implemented at time equals 20 seconds. The motor input is shown in the top plot, and the FES inputs are shown in the bottom plot. Note for safety, the left quadricep had a pulse width saturation of 105 microseconds. In this figure, the actual cadence versus the desired cadence is shown in the top plot, and the bottom plot shows the cadence error and the position error. Note that for FES-Cycling, the position error is less important than the cadence error. As can be seen, the cadence errors are relatively small, and the cadence oscillated about the desired cadence. The FES and motor inputs over a single cycle are shown in this figure to demonstrate how both the motor and FES inputs switched on and off throughout the crank cycle. In conclusion, a delay compensating controller was developed for a switched, uncertain nonlinear dynamic system with an unknown time-varying input delay, and a time-varying estimate was utilized. Delay-dependent trigger conditions were developed to appropriately schedule the activation of muscle groups and the motor. For future work, experiments will be performed using different methods to estimate the delay and to compare the performance. Thank you, and if you have any questions, please address them to my email that is listed below at brendancallen@ufl.edu.